Hi everyone, today we're going to solve question number 221, maximal square. I'm going to give you 3 solutions. We're going to dive deep into all of them so we understand the thought process of coming up with these solutions and evolving the solutions. I think this is a critical step to make you succeed. So let's dive into it. Given a 2D binary matrix filled with zeros and ones, find the largest square containing only ones and return its area. Essentially, you're given a matrix filled with zeros and ones, and your goal is to identify a collection of ones that form the largest square. Alright, let's look at an example. So given a matrix here, how would you identify the largest square? So one of the first things you probably want to do is identify if a particular cell contains a 1, right? Once it contains a 1, you might think about, alright, is this one part of my square? Now, if I look at it this way, the brute force way to solve this would be to check my partner, see if it's equal to 1, or go up to the part where it equals to 1. And then if it stops at this point, I know that this can be potentially a size 2 of 2. Therefore, my next iteration will check, I'm going to check my rows now to see if this and this is going to be equal to 2. In this case, it doesn't because the 0 throws it off, so therefore this is an invalid 2 by 2. However, it is a valid 1 by 1, right? So we go and iterate and do this operation over and over and over and over again until we reach to a point somewhere like this, right? Where we could go and check, okay, I'm going to go here up to the point where it ends, right? So this is a size 3 and can potentially be a 3 by 3. But once over here, we know that, then we're going to check 3 at my first coordinate. Okay, that's valid. And then I'm going to check my second segment. Oh wait, I got rejected by the third element, right? So this is probably not going to be a 3 by 3. So what do? I resort back into my 2 by 2, a potential 2 by 2, and then check whether or not it's a 2 by 2. And yes, it can be a 2 by 2. So therefore, this 2 by 2 can potentially be a positive solution, right? And you continue this algorithm and you'll probably get 3 different sets of 2 by 2. But since this problem involves only one solution, you could just take the first one or any of these and return it and it should be fine. This method is probably called, if you think about it, it's really brute forcey, right? You're basically reiterating and recalculating a lot of steps over and over again, and it won't be as effective because when you think about it, in the worst case scenario, you're going to be iterating through all columns and rows, causing a time complexity of O of row and column squared. This is pretty bad, right? So why don't we think of another potential solution and see if we can get any hints from the actual questions again. So if we look at the question briefly for a sec, one of the key points I mentioned here is find the largest square. So if you start doing these questions quite often, you'll start noticing some small slight patterns. If something that talks about largest, maximum, minimum, that type of nature, you could almost think about or at least consider using dynamic programming as a possible solution. Why I say this is primarily driven by dynamic programming is essentially using your history or a cache of some sort of knowledge that you know to build up your current solution, right? So we could try to break this problem into sub little problems or little smaller things, right? So let's look at this problem here. And instead of like factoring or finding the biggest possible square, why don't we isolate like one possibility, which is a 2 by 2, a simple 2 by 2, right? If you look at this quadrant right here, right? I'm gonna pick cup here. We're given basically a left top, a left quadrant, and a top quadrant, and a bottom quadrant, bottom right. So we have like these 4 quadrants, right? So if we look at this question, we have to almost think about, all right, if we want to apply, I don't know what to do. I know that's longest, so somewhat dynamic programming-ish. What can we do such that when we iterate through each item, we're going to actually have a ability to view our historical basically patterns and apply it to our future outcome. Now, let's assume that, okay, well, if we're going to do dynamic programming, maybe something we could do is maybe create a duplicate copy of this particular this matrix, but like this copy doesn't have to be actual values, it could be like all zeros. Let me just zero it all out. At least it is of the same size, right? So when I iterate through this matrix, as long as it hits 1, we're gonna do something on our cache, right? And what is this cache gonna really represent? Because we want to use, as we iterate through all these elements, we want to make sure that as we iterate, we capture certain elements over again so we can use to our next problem. One of the things I like to think about is that, okay, so the first approach we took, we essentially assume that the first variable is the left top option, right? Because we're saying that, okay, on the brute force method, we're going to go from here, top left, and then start going searching, right? So let's think a little bit outside the box. If we were to continue using the top left portion, the minute we go to the next box here, we lose track of pretty much what's on or some little bit of our history, right? So what we want to do potentially here is actually assume this particular quadrant to be potentially the bottom right, right? By assuming that this can be possibly a bottom right solution, then the problem becomes, as we iterate through these questions, we're gonna assume like, okay, well, this quadrant, so let's do an example. For example, if we go here, all right, what is this, right? We hit 1, and we're gonna see like, okay, well, my top left, and my left, they're all unidentified. However, it says it's 1, right? Size 1. So we know for a fact that the maximum size of this particular square on this particular space can be only 1, right? So the bottom right corner of this, imagine there's a square here, the bottom right would be 1, right? Same thing applies here. We're gonna assume that, okay, well, although my left is gonna be at 1, my left top, or top left, I think we call this top left because it's easier. My top left is unidentified, my top is also unidentified, however this is still 1, so I could, take the minimum of these 3 elements plus a 1 here, so my maximum size over here is 1. We're going to repeat this going on and on and on, and up to here it's also going to be 1, and we continue to go on and on and on. This will also be a 1 because if you look at the top left here, this is going to be 0 and this will be a 1, this could be a 1 as well, 1, 0, and this will be a 1 because we're doing the same thing again. Now, when we reach to this point, it gets slightly interesting because when we look at what was our bottom right corners of the previous 3 boxes around us, there are 1, 1, and 1s. These are 1 by 1s. Because I'm over here, I could take the minimum of these 3 elements, which is going to be 1, and add to itself over here. So this is saying that, okay, since this is a storage of all the bottom rights, this particular box at this particular point is part of a 2 by 2, right? So we know that there is a point over here that's a 2 by 2. So that we can store this as our maximum for now because, this is the biggest box. And we continue to do this algorithm. Go here, same thing again. Minimum of these 3 is 1, and you add yourself will be equal to 2. All right, we go down here, 2 unidentified and a 0. Well, that's going to be 0, and this will be a 1, right? So same thing here. Because of this 0, this is going to be a 1. 0, 0, 0, and 1 over here. And of course, this is the same pattern as the top one. It'll be a 2, right? So now we see a way of effectively identifying the maximum size of the potential square. It could be by identifying or storing bottom right quadrants, right? Or bottom right segments that indicate how big the box can be, right? But what we really just did here is, trade off a little bit of time complexity, but increased or juiced up our space complexity, right? This is cool. Sometimes, in the interview, they're cool with it. Storage is cheap. They may not care. However, if you ever noticed that this question, if you think deeper, there might actually be a way to optimize this just ever so slightly as well. Because the nature of the problem asks only for the maximum square, it doesn't ask anything else, storing any like where all of them locate, etc., etc. It only asks for one number. We can start thinking about potentially optimizing it even more. Now, before I go and talk about that particular problem, I just want to reiterate that I'll probably, after this segment, go and code up this particular solution, because a lot of the time, we may not even have the time to think about this deeper problem, right? Or the deeper solution, right? So sometimes you want to like, this is already optimized enough. We want to get into whiteboard, talk to the interviewer, seeing if they're cool with it. Most likely they'll be like, yeah, cool with it. And then we could start building up, okay, maybe you could optimize that at a later time, right? So after this particular solution, which I'm going to discuss, we're going to go and code up pretty much two solutions, right? This one and a more optimized solution. So on this one, just for your reference, this will be a O of basically columns times row time complexity, right? With a storage space of O or column and M as well, right? So when we look at this question slightly deeper, we can actually identify a small pattern, because as we look through these elements, we actually don't need to track all the matrix itself. If you think a little bit slightly more, we really only need to know what the size, or create an array or a cache that is of size the column length. Now let's look at how I'm going to explain this. So when we go through the exercise of looking at things, we can actually just create a cache of size of the same size of the column, and this will effectively be able to capture our previous elements, and also as long as we store the top left corner somewhere, the previous element, then we can pretty much formulate the expected bottom right corner, right, on here. So maybe it's a little bit convoluted. I can't explain it that detail right now, but maybe as we go through an example here and how the computer can compute it, it'll probably catch on. So in this particular algorithm, it really talks about the whole concept of, okay, I'm gonna go and try to do and look at my, what was my historical, what did I see before, right? And compute, okay, what I've saw before, and also my neighbor, and what the neighbors before was, do they form a square for me, right? In this case, it will not. It will just be a 1, 1, and a 0, 0, right? When it hits 1, and 1, 1, 0, 0, so what we would probably do, if it hits 1, the first thing you want to do is like your previous one, I'm going to store this as a temporary value first, right? Because that's my value here. And then I'm going to go, okay, because it's my temporary value, I'm going to start checking these elements, which right now they're not set to anything because I'm looking at the top left quadrant. So I can only know that I can set myself, which is going to be a 1. So that's fine. And before we move on to the next element, I'm going to make sure that I store this particular element call it as a previous, because now if we look at the context of this particular square, right, this is going to be previous to it, right? So let's go continue on. If I go to this next square right here, right, we're going to basically ask ourselves, all right, what was the previous, we're going to go through this again, store this one in here as a temporary value, and we're looking at this particular column. We're going to look at what was stored on the top, which is nothing. On the left is a 1, and the previous to the 1 was a 1. The lowest, because of this unidentified, these three will cause it to be only a 1. So that's fine. And then of course this one is a 0 and a 0, right? So this is like the first row, right? Now let's look what happens on the second row. The second row, because we're looking at a 0 here, and we're going to set our temporary value to be 0 there, we know for a fact that, okay, this is not going to be a square anymore, right? Because you're starting at 0. So actually what we're storing here bottom right is going to be a 0, which this will become a 0 as well, and 0. So actually let me make this as so it's more clear. This is like step 1, right? And there's step 2 would be a 0, 0, right? So this is the second step of the second row. And then the third one would be like, okay, well now I'm going to go to my my fourth case right here. So I reach up to here, right, which is at this point. And these three over here obviously is my previous value was a 0, and my temp value is a 0, and my next door neighbor is a 0, and itself is a 0. Then therefore this is going to be only a 1, right? Because we're on this row right now, right? So let me repeat that. So when we look at the matrix and look at the number 1, what we want to do is effectively look at what we saw in the past, right? On the past, at the existing same position over here, the past was this is like our past right here. Before I started editing anything else in here, this was the past, right? We're just overwriting the past. So in the past, this was a 0. It didn't mean anything. However, when I look at my past plus my previous past, or like our partner's past, to see if there's anything that has a 1 in there, and there's nothing. So therefore, it's the same concept, right? This is only going to be a 1. Same thing goes into this case and this case, right? Because if we look at our history, you know, they're all 0s, and we look at our neighbors. In this case, though, our neighbor is a 1. However, its past was like only a 0, right? So therefore, and my past was also a 0. So therefore, looking at these consideration, this is only going to be itself, which is 1, right? And then we move to the next cache. Remember, these are not creating new instances of the array. All we're really doing is actually, you know, I want to show you each step of the process, why this would work, right? So on the next phase, we're moving on to this row, right? So in here, it's a 0, it doesn't do anything. But on here, this is where it gets interesting, right? On here, we're gonna look at, okay, what was before we start, it'll be like, okay, I'm gonna temporarily store my 1 here, right? I'm gonna start looking at, okay, so on this particular value, what was my partner here on the side? It's a 0, right? And what was my partner's, his past, right? That was, you know, previous right here. So that was a 0 here. And what was my past? My past was a 1, right? But when I take the minimum of these 3 elements, right? So we know that my 1 is, you know, I mean 0 is the minimum. So therefore, this whole thing is maximum be a 1 by 1. So I'm gonna put a 1 here, right? Now, if I do that, I make sure I go update my previous. Now, because this becomes my previous, now we look at this particular element. This is the one that's very interesting, because now when we go and enter this particular quadrant, we put the 1 in our temporary storage, and we start looking at, okay, well, what is my left partner? My left partner is a 1, right? And because this is a little bit lagging, we can check what was the previous to this left partner, which is this element, which is a 1. That's great. And what was my historical value? Well, it's right there, right? This was what was my past, right? What we looked at before. So therefore, I have 3 of them that equal to 1. So what I could effectively do is like take those 1, the minimum of those 3 elements, and add 1 to it. So this will be a 2. And then same case for here, another 2, right? And then we move on to here. Of course, this is a 2. You can always put a value on the side saying like what as a solution, you know, store that. So your maximum solution right now will be a 2. And then we go to here. In this case, it's going to be like, okay, well, 1 is going to be a 1 here, over here, because you're looking at your past. I'm not keeping track of this, but okay, my 1 here, that's great. We're looking here. Effectively, it was your past was like a 0, 0, and a 1 and 1. So this will be just a 0 over here. So the max is going to be a 1. And on this element, oops, actually, let me create this new one because that's not the new instance. This is the new instance. So this was 0. Sorry, apologize for that. I'm not going to edit this out. So this is the row that we're going to look at for this particular element, right? So we look in here. That's a 1 because we look at our previous history. Boom, there's nothing there. Our partner is nothing. It's nothing there, and our previous is like only a 1, which doesn't mean anything. So this is a B1, and we go continue on. We're gonna look at our previous historical value, which is a 1. That's cool. Checkbox. Our next door neighbor. That's cool. However, our previous, which is a 0, that's not cool. So therefore, my minimum will be a 0, and this will be defaulted to 1. Now let's take a look at this one. This one is kind of interesting because it's a 0, right? So we can't really do anything. If it is a 0, then there can't be a box bigger than that, right? So this will be auto-defined by 0 and 0. So our previous are 0 now. Yay, we're 0'd up. And now for the final step, we go move down, boom. We start modifying the same array, but we only have like a couple of values, right? So on here, we're gonna look at it. It's gonna be a 1 again because the same logic applies. Boom. But when we get to this point, we look at 1, 1, and 1, right? This one doesn't. This one, remember, this is only an instance of itself. So this one is equivalent to here, right? So this is cool. Left is cool, and our previous should be a 1 because we were here before. When we look at the previous is cool, so this will actually be a 2, right? So effectively doing this, you'll find the solution again, right? I know this is slightly a bit confusing, but when we look in the actual code, it'll probably make more sense. But let's just recap real quick, because right now we've just eliminated all of the rows and times complexity wise and only kept it in the column size, right? So all you're really doing, if you've done a question like the histogram problem before, this is very similar. All you're really doing is taking layer by layer by layer by layer and using the layering as you go iterate through each row, that as your historical point, right? Like at that particular first layer, this is my history, right? And then I go to my second layer, so that was my past, right? Before I'm gonna overwrite things with zeros and then go on and so on and so forth. And that's all you're really updating, right? So as you go boom, 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 update, look at your past and form the squares, you could find the maximum squares, and therefore you could, report and get the right solution. So let's dive into code. I've been talking too much, and let's see if we can actually start solving this, okay? All right, let's finally get into some coding. So the first problem I'm gonna code up is, well, not problem, solution, is the dynamic programming, using dynamic programming, and it's the matrix solution. First of all, I'm going to convert this % back into function matrix because syntactically I like this more. And I'm going to start creating a couple of variables. So let's create a cache, that stores our stuff. And we're going to call this cache, I'm going to actually make the cache a duplicate copy of our existing matrix. You don't need to do this. You could simply get a new cache of 0 values. It's the same thing, but I just feel like filling things in there and replacing it, doesn't harm it. You could always do it either way. I'm going to go create a height, so I don't have to reference it all the time. It'll be matrix.length. The width will be equals matrix at 0 dot length, right? And I'm gonna create a solution. For now, I'm gonna call it 0, right? And okay, cool. So actually, let's pick a pause here. We can't actually put it as 0 because there is a case where what if we don't get a matrix that is beyond that is more than 2 rows, right? What if it's only 1 row? And if it's only 1 row, then we really only need to consider if that row contains, a 1, because the maximum square you can have in a 1 by 1 or 1 row is 1, right? So instead of 0, I'm gonna actually make it such that I'm gonna go math.max and spread the matrix at 0. So for those who don't know what the spread operator does, all it effectively does is take your array here as an example, takes this array of arrays, array, right? All this really does is this is matrix, right? So all I'm doing is just taking everything in this element and copying it or spreading it into here, into this array. So effectively, you're just taking the guts of this inner part of the matrix and plopping it in here, right? So same thing in here, I'm just taking the guts of the 0th element, right? I'm gonna take the maximum value of that element. So in here it could be 0, 1, 0, 1, etc., etc. All I'm doing is just taking the guts of this, and putting it in here. So you'll see like the maximum value of those, right? Okay, so that's all I'm really doing. This is only to deal with the edge case of the first, if your input's gonna be like of size 1, right? So I'll deal with that. That's great. And I need to also consider some elements that, because we're dealing with those square boxes, we don't actually deal with the first row. So I'm gonna make sure that I capture that. So for let I equals to 0, I is less than matrix dot length, right? And I is plus plus. All right. So what am I doing here? All I'm doing here is to check whether or not my sidebars here, like if I were to give like those odd cases where, you know, everything else is 0 and all my first initial bar is 1, I need to make sure that, hey, does that contain a 1? Alright, so all I need to do is like saying solution. These are like dealing with those edge cases. Math.max is going to be compared to your solution. And I'm going to look at the matrix at ith position, but I'm only looking at the first value. So this deals with that really unique case of, okay, what if all of these inner elements were zeros and everything else is 0, but you have this like one little awkward one on the top, on the bottom left corner, right? Then this one's going to be very difficult to solve. So that deals with that case. So all we have to worry about is like this inner box right here now, right? So let's go look into it. I'm going to first of all write a mark, bring back the old school for loop. Let row equal to 1, because I want to start at this position, because I've already dealt with the ones on the edge and on the side edge as well with these two additions. I'm going to start it with 1. So row is less than height, right? And row will be plus plus. Great. For every row, I'm going to check for every column. Let column equal to 1, and column is going to be less than width, right? And then column is going to be plus plus. So what do you do here? All right, so as we iterate through each element or through each number, I'm going to check if my matrix at that particular row and at that particular column, does that equal to a 1, right? If it does, then we better do something with it, right? In here, remember what I mentioned before on our quick example here, we need to ensure that we're looking at the top, left, and those 3 numbers and take the minimum of it, right? So we're gonna do that here. So here we're gonna go and say our cache at that particular position, row and column. Ah, jeez, can't type right now. Getting late. Row and column will equal to math.min, right? And then we're gonna make sure I'm gonna check out the minimum of the cache, right? At position of row -1 and of column, right? And I'm gonna make sure I go to cache at row and my column -1 and my cache at row -1, column -1, right? And I believe that's cool, and I need to make sure I add 1 to it, right, to itself, because that's what you need to do. And then from here, I need to make sure that my solution is equals to math.max of what was stored in the cache at row and column, and of course compare it to itself, right, which is the maximum, and then store that. Cool. So when we look at this, have we solved the problem yet? We're missing some elements. What if, because there's no edge, they never put any notes here saying that, okay, what if I give you like these edge cases, which is, what if the matrix I give you is null, or what if the matrix I give you has like nothing, right? So I'm gonna put a condition to check those conditions. So I'm gonna make sure that my matrix actually does exist, right? If it doesn't exist, or if my matrix at that position 0 does not, then I'm just gonna return back 0. So it's getting late. All right, it's cool. Let's see if this solution works or not. Let's run the first case. Oh, one thing I almost forgot. I forgot to return the solution. Return solution times solution. Great. Let's submit it. and bam. Ooh, this is terrible timing, but it solves the problem, right? Let's run it again. Let's run it again just to make sure. I like to take a heat check. Oh well, you know, this is really LeetCode. You're really reliable. So this is the answer to the first solution, which is goes into, you know, creating squares and etc, etc, etc. Now let's dive into a little bit more deeper question here, like how to solve that one. So when we talk to the interviewer, we're like, okay, how can we optimize this, right? What's the big bottleneck that we're trying to optimize? So what we're trying to optimize is pretty much our storage layer, right? So in our storage layer, we're actually optimizing this, the cache itself, and this syntax down here, right? So actually, when we look at this particular problem, we don't actually have to edit that much, right? All we really need to do is effectively create a cache, you know, change the cache to now to be of size, you know, it's gonna be a new array of size width. Oops, move this down here because width hasn't been defined yet. There we go. Okay, I'm gonna make it size width, and I'm gonna add 1 to it. The reason why I want to add 1 to it, if you guys didn't know the subtleness I had here, if I didn't add a 1 here, it's gonna be unidentified, which is not cool, because I'm going to check on this top quarter what was my previous partner. It was nothing. Just for argument's sake, I'm just going to make an array that's size 1 bigger, and so I can check the next side and so it exists. So that's what I'm going to do to save that unidentified problem. So that's why I put the +1, and I'm just going to fill it with zeros. You know how I talked about how you don't have to carbon copy, you could just fill. There you go, you can fill it. So right now I just filled it up. That's great. The same condition still applies, you know, those edge cases still apply. However, now we don't have to check this anymore because we don't have to go check those edge columns. This still applies because we're still iterating through everything, right? But now one thing that is changing is that we're gonna make sure to start at position 1, but our matrix is gonna actually be -1, -1. Because we've already grown this particular cache to be a +1 more. So we need to make sure that we get back to 0, 0. All right, cool. So now I'm not dealing with rows, I'm dealing with caches, and I'm only gonna have columns, right? So that's all, yeah. I'm only dealing with columns, right? So one part we need to change is this formula, right? Instead of looking at the 2D matrix that I have, I need to make sure I'm looking at a couple other elements. So remember what I mentioned earlier before, how I need to, you know, before I do anything, I'm going to check my value, or at least create a temporary value. Temporary will equal to effectively my cache right now, the column, right? And if it equals to, oops, if it equals to that, you do something in here, else I'm going to make my cache at that column equal to 0, right, to clear it out, and make sure that my previous will equal to my, oh, I didn't define my previous. Let's define it here. Previous equals to 0 for now. So previous will be equal to temporary. Cool. And over here, I am going to have to change something in here, right? The thing we change in here is that we're not referring to a full 2-dimensional array anymore. We're going to do it by one by one. And what we actually have available instead to us are these variables that we store that are available to us. So in here, I'm simply just going to go and check. Let's delete this. All I'm really going to check is my first one, my previous value, which is available here. That talks about basically top left corner, right? And then I'm going to compare it to my cache at column -1, which is my next door neighbor, I call it. And I'm going to check my previous one, which is going to be my top, right? Cache at column, right? We'll check these 3 values, and then I'm going to +1 to it as well, right? And let me just get this to column. And effectively, by doing this, we saved a lot of rows. We don't have to do that much now. Now let's try to submit the solution and see if it actually solves the problem. Oh no, it failed. What did I do wrong here? Something failed here. So this is where you have to sometimes troubleshoot and see what you've done wrong. Okay, cool. Let's see. If I follow through my question here and see if I have the right thing. Okay, that's fine. That's fine. Let's see, what did I screw up on? Oh, ha. So we never actually go end because we created that extra space here. We forgot to go all the way to the end. But here we go. And now we should be good. All right, see this problem, this new solution, it beats 100% of storage space because we don't have to store that much anymore. And it's also, you know, pretty fast. Just changing a couple codes. So some of these questions are relatively typical to be asked on an interview because all you need to do is change a couple of elements on your existing code when you optimize things. And yeah, hopefully you find this useful. I know this is a little bit more drawn out video, but I think if you spend some time to understand this particular concept and this particular question, you're going to be able to solve a lot of questions. Anything relating to like histograms, anything relating to finding maximum square, finding the maximum rectangles, maximum stars on grids. This is very important. So hope you like it. If you liked it, please subscribe, please hit the bell. It's getting really late here. It's like 1 a.m. and I'm getting tired and I'm probably didn't explain stuff at the end that well, but please bear with me. Let me know what's improvements and we'll stay tuned for the next video. Thanks everyone.